Hey guys, in this video we will go through the Leetcode 98 to get a validate a BST. So what is the BST? The definition is as it is right here. So the left subtree of the node is contain only nodes that is strictly less than the node key. It says node key, that means node value. And the right subtree will be strictly greater than the root node's value, and also both the left subtree and right subtree itself has to be a BST. So let's look at the example in here. I don't think it's a great example, but let's take a look at what is available. So for this BST, the left number has to be less than the root node, which is 2 in this case, and the right subtree, the number has to be greater than the root node, in this case 2 again. So this is a valid BST, that's why you return the 2. And in this case, left, the number on the left is smaller, so it's fine. The number on the right is bigger, and it's not bigger, that's why it's not fine. And so this is a false. So another thing to notice is that all the number on the right, so 3, 4, and 6 has to be greater than 5. In this case, it's not, because it's smaller than 5. That's why it's not a BST. So basically, all the number on the right has to be greater than the root number, and all the number on the left has to be smaller than that number. So, and that rule applies to the subtree as well. So all the number on the right for this subtree has to be greater than number, and also all the number on the left has to be smaller than that number. So that's the rule in order to make it a valid BST. And this question was very popular, right? It was asked by that many companies. So I'm going to solve this problem using 2 approaches. The first approach, we will use a recursion approach. So we look at the boundary of the number, and we have a lower bound and upper bound. So for example, the first guy, the lower bound, so the root can be anything. The root number can be anything. That's why it has no lower bound, has no upper bound. That's why it's negative infinity and plus infinity for the upper bound. And for the number on the left, the lower bound is the same as the upper bound in here, and the upper bound will be the same as the number at the root node. And then for this guy over here, which is a child node of the 5, so the lower bound will be the same. The upper bound will be the value. And for this one, which is on the right of the 5, right? So, and then the lower bound would be the same as that number, and the upper bound will be the same as that upper bound. So that's the pattern, right? So this is the key to break into this approach. So on the other hand, on the right hand side of the bigger tree, the lower bound will be the same as that number, and the upper bound will be the same as the upper bound of the root node. When we go down, and the upper bound is the same as the upper bound of the parents. So as you can see, on the right hand side, upper bound is always the same as parent. On the left hand side, the lower bound is always the same as the parent. Okay, and in this case, the lower bound is the same as that number. However, 13 is greater than the lower bound. That's why this is not. So this is why this is not a valid BST. Not valid. And we will use this logic to implement a recursion function. So let me zoom in a little bit. We need a recursion function, which is a helper function for recursion. If the root node is a none, so that means it's nothing in it, and this is a trivial case, and then just return a false, return a true for that case. And then now we are comparing, is that number greater than the lower bound, and is that number is less than the upper bound? If any one of that condition is not met, we return a false, right? That's why we put a not in front of the condition. And if this one does not return, and then we move on, and then we check the left branch and the right branch. If both of them return a true, and the whole thing return a true, because in order to be a valid BST for the entire tree, we need the left branch itself is a BST. Also, the right branch itself is also a BST. That's why we need an AND to connect the two. And so this is exactly what we went through, right? So the root will be the root dot left, and the lower bound will be inherent from the parent, because we're looking at let me go back. We're looking on the left-hand side, right? So the lower bound will be inherent from the parent, which is exactly the same, which is negative infinity. And I mean, negative infinity on the leftmost branch, right? But in this case, it's not negative infinity anymore, okay? And for upper bound, it's basically the value of the root of the parent. So basically, as you can see, the upper bound in this case is the value of the parent, and this case, the upper bound is the value of the parents as well, and also in this case as well. Sorry, in this case, this is on the right branch, and we will talk about. So it's all applied to the left branch for now. And now we go to the right branch. So the root will be root dot right, because we're looking at the right branch. Lower bound is the value of the root. Upper bound will be inherent from that parent. So look at this graph again. Upper bound is from the parent, same upper bound, they are sharing the same upper bound. Lower bound is the number of the parent, right? So lower bound is the 10, lower bound is 15, which is the parent of this guy over here. Same for this one, right? So this is the right branch of this guy. Lower bound is the same number of that parent. Upper bound is being shared, right, with the parents. Okay, and we can run that, and it is pretty efficient, right? So in terms of time complexity, it's big O of n, because we just basically traverse all the possible nodes. And for space complexity, it comes from the stack, the recursion stack. So in the worst case, where if the tree is completely imbalanced, it looks like a linked node. So let's say if the trees only have this branch, right, only this. In that case, the recursion stack will be big O of n. That will be the worst case, because we have to wait for the next one to finish before we can finish the current one. So for space complexity, it's big O of n as well. So this is the approach for the recursion method, and I'm gonna implement it. I'm gonna solve this problem using the level order traversal, the Inorder traversal as well. That will be using a stack. And let me pause the video. So this graph shows the algorithm for the Inorder traversal. So we first go to the most left one, and then go to the root node, and then go to the right one, and then we go back to the root of all the roots, and I'll go to the right, and then go to left. Here there's nothing, so that's why I go to the right. So if we traverse the tree in this order, notice that it's increasing order, right? 3, and then it's less than 5, 5 is less than 7, 7 is less than 10, 10 is less than 15, and 13 is less, should be great. I mean, this number should be greater than this number. That's why this is not a BST. And also we have a variable named pref that keep track of the prior number. So at the beginning, the pref is equal to negative infinity. And when we are here, the pref will be 3. And then when we are here, and then we compared 5 with the pref, which is 3, and it's greater than 3, so it's fine. And then we update the pref, now it's 5. And then we are here, and then we compare this number with the 5, which is greater, which is fine. We update that, becomes 7. And then we are here, and then you compare 10 with the 7, 10 is greater than 7, which is fine. So we update the pref, becomes 10 right now, etc. So whenever we traverse the tree, we compare that number with the previous number to see if that's greater than previous number. If that's the case, which is fine, and then we update the previous number becomes the current number. And then let me show you how we can implement the Inorder tree traversal. So we first have a stack. We will use a DFS, and we have a temp root, which we will be working with the current temporary root that we will be working with. So the temporary root right now is just the root itself. The pref at the beginning will be negative infinity, and while the stack is not empty, or there's something to be assigned to be the temporary root, and we will execute the following. And this block of code is basically collecting all the numbers on the left hand side. So basically, while there's something in the temporary root, we will append it to the stack and then keep going to the left. So temp root at the beginning will be this root, and then go to the left, and then append it, and go to the left, append it again, and when we go to the left, which is nothing, and that's where we will exit from this while loop. And if there is something in the stack, we'll assign it to the temporary root, pop it off, and then this is where we do the comparison and also update the previous number. After that, we look at the right branch. In this case, there's nothing in the right branch, so we jump back to here. So the current temp root will be none because there's nothing on the right branch. So this one will not be executed. And there's something in the stack, however, and then we will pop it off. So right now the temp root will be the 5, and then we do the comparison to the prior number, and then look at the right branch, which is 7 right now. So temp root right is 7. Yeah, temp root right now is 7. So come back to here to see are there any left child for the 7, which is none. And then we go back to the 5 by popping it off. Sorry, we are not going to go back to 5. We're going back to the stack right now has the 10. So go back to 10 and then do the comparison with the previous number, which is 7. And then we update the previous number as well. And after we finish the 10, the stack will be empty. But there is something on the temporary root, because the temporary root right now is the right node, which is this guy over here. And then we go search for the left branch, which is nothing. So that's why we skip the entire while loop. And because right now the stack is empty. That's why we don't do this if statement. Also, when then we do the comparison with the 15 with the prime number, which is greater than the prime number, which is fine. And then we go to the right, which is 13. And there's currently nothing in the stack. And the temporary root right now is not none, so we will go down. And there's nothing on the left for the 13. That's why we don't execute the while loop. The stack right now is empty, and when we do a comparison, and this is where we will return a false because it's less than the prime number. Just submit that. Looks really efficient. So the time complexity is also big over n, same as before. As the recursion, for space complexity is also big over n, because when the stack for the completely imbalanced tree, that will be big over n. That's the worst case scenario. And this is so much for this solution. I hope you like it. If you do, please like this video and consider subscribing to the channel. That will be a huge encouragement to me to make future videos like this. And thank you for watching. I will see you in the next video.